Let's look at the first GNN filter which has been generated. The idea there is to update features in each iteration by using the features of neighboring nodes. Particularly in this particular kind of filter, it was designed for a model specific for a graph where each node Vi is associated with labels Li, which are initial labels, and certain feature Fi. Remember that we want to often use features to be modified, not labels. So typically labels remain the constant term. And here then we can apply this filter G, which not only involves the feature associated with neighbors, but also the label associated with each node for which we are filtering and neighboring node, and the summation over all the neighbors. So G, which is GNN filter, has a two interesting property. It is a local transition function because we are looking at the neighborhood of the particular nodes when we want to filter and improve our features. And it involves node with from one hop neighborhood. That's a interesting other property because we are looking at local transition function. Another interesting aspect here is that we can actually, as I told you, that SL and SG are the labels which remain constant, only the feature will change. We can use feed-forward neural network to model the G, and this G will remain same for all nodes, and hence it is shared by all the nodes in a single pass of the filter. And this is how we can actually develop a better filter or a first filter for graph neural networks. Now, if you look at very carefully, we have somehow used spatially localized information. Can we actually perform same kind of operations in a more systematic way? The graph stage filters are some similar kind of filters which are spatial based filters and can be used for graph filtering. In a spatial based filter like GNN earlier we saw, we are going to aggregate information from neighboring nodes. Here, the another aspects like GNN earlier, it is a shared aggregator. So aggregator remains same, and we are going to actually use each node to actually train the aggregator. Typically, it involves also one hop neighborhood. How it works? For a single node Vi in the graph, what we will do is we'll take S samples as the input from the neighborhood using some random sampling. So if I have a node and I have a neighboring nodes, typically one half, I'm trying to actually sample randomly a set of neighborhood. Once I have that, that's what this operation is. So at the end of the day, I will get a new set of neighbors, which are sampled set of neighbors. Now, I'll use these neighbors to generate new features through aggregation of all the features of these neighbors. So, what I'll do is I'll go take nodes which are actually in this particular set of sample neighbors, an aggregate feature for that to get my output filter f dash ns vi or generate a new features. Once I have this, I'm going to concatenate the filtered or a new generated features with existing feature of my node vi and apply a sigmoidal function to generate the output or updated feature for my ith node, which is f dash. Here I have to learn this parameter theta, which are unknown. So in a graph sage filter, I'll choose my single node vi. I will sample neighbors using random sampling and create a new set of sampled neighbors. Use these neighbors and aggregate all the features from these neighbors to generate a new filtered feature based on this set, which is nsvi, and then concatenate this feature with the original features and use them to actually as an input along with unknown parameter theta, apply sigmoidal activation and get my new updated feature f dash I for the vi node. In this particular case, sample function is defined well. Aggregate or aggregator is a function which we need to define. There are different kind of aggregators or aggregate functions have been defined in the literature. But before we go towards that, let's just understand very simplistic manner what aggregator does. Let's take this particular graph. We have 6 nodes and 3 feature for each node. The job of aggregators here, which is for a particular node, let's say Z, is to randomly choose. Here we have only one available sample, so we choose this sample and we also look at the sample of nodes connected with U and the aggregate and then update the sample of Z. So this now will become a new feature for or updated feature for Z. That's what aggregator does. Now let's look at how we can actually use different kind of aggregators, the aggregate function, to actually get updated features. In min aggregator, what we do is following. We take element-wise mean of all the feature vectors in this sampled neighbor set. So we actually just do element-wise averaging of all the features which are actually sampled in the first step. So here what we do is we take a weighted average of neighbor as a node representation and again we concatenate with the input features to get back our filtered features f dash I. The other aggregators people have used is LSTM aggregator. Here LSTM is used as a function approximator for the aggregator. We utilize LSTM long short term memory architecture and we represent the sample neighbor nodes nodes of vi as a nsvi and most importantly we represent it as a sequence. So I have a set of sample and I represent it as a sequence of nodes, and then I pass it to the LSTM as my input, and I then actually generate the feature, and the final output or last unit of LSTM actually provides me aggregated representation. How it works? Which is my FDES NSVI. In several papers, these sequences are actually in pooling operator. We use max pooling operation to summarize the information from a neighboring node. And before we actually summarize, what we do is we apply nonlinear activation function like alpha here to get my final output. Here, theta pool are the parameters that we have to obtain from the data. Now, we look at another filter, GAT filter or graph attention filter. Use self-attention mechanism to actually filter the signals. Here, we try to get information aggregation from the neighboring nodes for feature generations. However, unlike other like GCN filters, we also use a mechanism of attention in aggregating the information from neighboring nodes. What we try to do in a GAT filter is try to assess the importance of each neighbor around a particular neighbor and generate an importance score for all the neighbors. So let's say I have a Vi, I have a node Vj, I have a node Vl. Then the objective of graph attention is to try to give a score to each of these neighbor or corresponding features. Once I get these scores, the importance scores are used as a linear coefficient for aggregation function. Here the idea is that we can differentiate based on these scores the importance of different neighbors associated with particular node and weigh accordingly, or generate features accordingly in the case of filtering process. So how we can generate the importance score for any node? For example, I want to generate an importance score for node Vi. Then I will not only look at the neighboring node of Vi, but also Vi. So this is my set of nodes for which I want to generate importance score, including self-attention. And this can be calculated as this score calculator, which is Eij, the importance score between node Vi and Vj as a sum activation function. Here we have taken the leaky ReLU, where there are set of shared parameters. One shared parameter is theta, another shared parameter is A, and Fi and Fj are the feature vectors for the Vi and Vj nodes. And in this manner, we get a Eij, which is importance score. Once I have importance score, I have to actually use them for my filtering. Now, what we'll do is we will take this importance score and we renormalize them so that the output of representation will have a reasonable output in a particular range. Here we will use soft score normalization to actually compute alpha ij, which is a normalized score or importance score for node I and j. Once I have this alpha, I can always go and compute new representation of my node I. So look at this particular process through this graphical representation. Here I have taken a feature for ith node, which is fi, and feature for jth node, which is fj, and they are actually parameterized through they are multiplied with some certain set of parameter theta, and then the leaky value is applied where A are shared parameter, theta are also shared parameter, to obtain the alpha ij, which is a normalized score or softmax normalized score between nu I, vi and vj nodes. And once we have normalized score, the new representation, which is for the ith node, which is fi dash, can be actually represented as alpha ij fj theta. Now, often we want to actually stabilize the learning process of self-attention, and for that, instead of using a single attention, we will tend to use a multiple attention heads m and the different theta m and alpha j m. In this case, what will happen is that we'll apply same rule, but we have now, instead of having a single attention, we have multiple attention. So we will concatenate, the symbols indicate concatenation operation, and we'll actually combine them all, or some time we get a average output in terms of fi, that's using a multiple attention heads. Often we also have a feature associated with ages. So far we have not discussed about those age features. We always discuss about feature associated with nodes. We have discussed several examples in past which discusses that we do not have only node feature, but we have also age feature. For example, in a case of molecular graph, we have bond type, bond order, aromaticity, ring type. In case of social media network, we have a number of interactions, text messages between two nodes, browsing behavior on the same contents by two individuals. So the age feature becomes an important aspect of my graph, and for that I need to actually include age features in my filtering operation. Age feature, as I told you, provides not strength but also properties of relation between two nodes. Most approaches explicitly use node features, as we discussed. However, discard age feature which may contain important information. So question is, can we actually include edge features in our graph filtering? So in a message passing neural networks, which is a general framework for a spatial based filtering techniques like graph convolution neural network or graph attention network or graph sage networks, all of them are special cases of message passing neural networks. And message passing neural networks, which are we have seen so far, which are special cases of special cases, do not allow us to include the edge features. However, there are MPNN filter which updates its features, not only using the features of node but also use edge features if they are available. So in message passing neural network, we have a message passing function M. We have a feature associated with node Vi. We have a feature associated with node Fj, and we have edge features between node Vi and Vj. Remember that message passing neural network does not require to have edge features, but if we have edge features, we can actually incorporate them without losing any, without loss of any generality. So here message passing neural network will be filter will be used where M will sum over all the neighbors of node Vi, and we get message from neighborhood called Mi. Now this message which is received from different neighborhood of node Vi and which is summarized as a Mi will be actually will be used along with feature of Fi, and update function will take this as an input and generate updated feature for node Vi as a Fi dash. This allows us to include edge features seamlessly without any